So good evening, everyone, and welcome to today's session of Saturday Talk by JanyuTechnologies. We are privileged to have Professor Dr. Arunkumar Balkrishnan today for today's session. Professor Dr. Arunkumar has done his Bachelor of Science (BS) in Applied Science from PhD College of Technology in the year 1983, after which he completed his MSc in Applied Mathematics with specialization in computer science from PhD College of Technology in the year 1985. Today, Dr. Arun Kumarji is going to speak on the artificial intelligence and overview of its algorithms and applications. Sir, over to you from here.
I thank Bhimanyu sir and Senthil Vinayagam for this opportunity to talk to all of you. It's quite an esteemed set of people who have gathered over here. Really an honor for me to be talking to all of you and to be able to get in touch with you. Of course, wonderful that we also have old friends and batchmates from college in the same meeting over here. I'll take off the camera right now and only do a share of my presentation so that you're all able to visibly see it better. Yeah, so I do hope you can all see my desktop. I've already got sharing on. I hope you can all see it. If you can't, please do tell me. So this is an overview of artificial intelligence. I'd like to be talking about what is the area where AI really works on. I'll go through this very quickly rather than at a slow pace. Intelligence is actually very hard to describe. Most descriptions of intelligence has been from a performance perspective rather than talking about how it should really be created. So we say somebody is intelligent when the person does good activity. We don't really go back to how that person has been able to do good activity. I would like to also change this to say that intelligence is something that we observe and acknowledge when it is done in a new area. What do we mean by this word new area? A new area is one where we say the knowledge is still incomplete. So my definition for intelligence is the ability to work efficiently with incomplete and complex patterns. This is my definition of AI. You're free to interrupt me anytime. You can always come back to me with questions later on too, but if you want to interrupt, you're welcome to do that. So what is artificial intelligence then? Artificial intelligence is enabling computers to work efficiently with incomplete and complex patterns. Now, why is this a difficult thing? Why is it a challenge? When the patterns are incomplete and complex, the search space becomes very huge. It becomes a large, unbounded search space. This huge search space, when we try to search it in a normal algorithmic manner, this takes a lot of time, or what we call as non-polynomial time complexity. NP complete, NP hard is what we say in the terminology. In other words, it's something that is an exponential time, meaning for a small increase in the amount of data, the time increases exponentially. Now, patterns by themselves are what we call as a set of repeating significant attributes. So how do you measure the complexity of a particular pattern? A pattern's complexity is seen by the number of attributes in the pattern and the relationships between these attributes. The more these attributes, the more the complex. The more relationships between or these attributes, meaning that interdependency, complexity increases. I normally take this a little slow, but I think due to lack of time, we just go through this. I look at the world as being in three segments. Segment one is what we call a totally known segment. All knowledge in this particular segment is known. For example, how do you find square root of a particular number? How do you do certain things like starting a particular fan? You can press a switch, it works. Therefore, the problems in these domains, there is a method that exists for all these problems. When the method is existing for all the problems, we ignore the underlying knowledge. We ignore the underlying patterns. The solutions over here are more method-oriented. We create a method and you find the answer for that. Going to the other extreme of these three segments, we have a segment that is totally unknown. Hardly anything is known about these. For example, do we have life after death? Do we have life on other planets? All these become questions that are still just being hypothesized rather than actually we have any actual data about. So both these areas, segment 1 and segment 3, is not the area where AI is going to be applied. So we go down to segment 2 now, which is partially known. We know a little bit, rather we know quite a lot of everything, but not everything is known. So since everything is not known here, the patterns here are incomplete is what you say. That means the number of attributes in a pattern and the way these patterns interact in the attributes wise are not known to us. They're incomplete, and how they behave is not very known to us. So this is an area where you're forced to work at manipulating the patterns themselves. An example is diagnosing diseases. Well, some years back, you did not know that there was something called a coronavirus and a disease for that. This happened. We are still trying to explore how the chromosomes in our body really interact and come back, the ACTG, and how they interact and how they come back is something difficult to understand. Similar way, there are a lot of areas otherwise in engineering even where we find that the complete knowledge is not there. This is the area where we say intelligence is required. So intelligence is definitely required to handle problems in this partially known domain. An algorithmic approach cannot work here because algorithms by definition are definite. So definite becomes just the opposite of ambiguous. So it's also a fact that in the world around, as we keep acquiring more and more knowledge about things, items that are there in segment 2 start moving to segment 1. And items in segment 3 also move down to segment 2. So whatever items, as we get to know more about things, we are able to move things. So today we have traveled to other planets too, and we get some idea about that. The moon is something that we are able to go to. We have even gone to the dark side of the moon and we have landed there. So we seem to know a lot more about it. It's definitely not in segment 3. It is more to segment 2, if not getting to segment 1. It's knowledge-based systems is trying to make it less search and more of using knowledge to reduce the search area. So the primary things in a knowledge-based systems become the knowledge base, acquiring the knowledge base and representing it, and inference engine. This is a new one now. So inference engine says, given some evidence, using the knowledge, what action can I do? There'll be a user interface here which can get knowledge and which can get inputs about what is the environment outside there and how the system could actually give back the result also. There's also another new component called a knowledge acquisition model. How do I get this knowledge from a human expert? One is in knowledge engineering, where you have a knowledge engineer talking to the expert and actually encoding all the knowledge. The second approach is what we talk about today as machine learning. So machine learning becomes a way of acquiring this particular knowledge. How do you represent this knowledge? The first thing is this knowledge representation. The matter of fact, this is a very important part and it's not given enough emphasis today. If you don't represent the knowledge well enough, the whole thing goes wrong. The simplest one is the production rule. We talk about if some condition is true, then do some activity. This is what is called a production rule. What do we call this production rule? It's taking the same idea as to how we talk about grammars, where a production rule will tell you that given a non-terminal, you can expand that into a terminal and then into another non-terminal. We talk about a more practical example here. If the car in the morning is not starting, what do? The first thing you check is, of course, whether there's fuel in your car. Next thing that you will see is whether the battery is down. How do you check it out? By pressing the horn. So if the car does not start, check the battery by pressing the horn becomes an if-then rule. Now, all knowledge, all AI is ambiguous. So this will not be talking about a definite action to do. If the car does not start, is talking about you tried it 10 times or did you try it 100 times? Yeah, you tried 2-3 times and doesn't start. Is it 2 or 3 or 5 or 7? We don't know. If it's going to be a very cold area, maybe it must put on the heater. There are multiple other things that come into play. It doesn't become as simple as doing what is given in this particular slide. There's an ambiguity in the input. So understanding the problem becomes ambiguous. The action also is not easy to do. The result is again not deterministic. Every time the result will not be as expected. Another way of representing the knowledge becomes what is called a semantic network. A semantic network has got a set of nodes and links between them. For example, if you have a situation of yellow eyes and fever and the urine is also yellow, these three nodes link together and say the disease may be jaundice. This is how you're talking about a semantic network. Semantic network represents knowledge in a much better way because you're really talking about what is causing what to happen rather than just what to do. So another example that you have over here is that you might have a man. A man has got hands and legs and therefore can walk. So man will be linked to hands and will be linked to legs, and then the ability to walk will be coming up over there. The relationship becomes has between man and hands and leg, and the ability to do things, or the can relationship can be walking. So we have nodes that represent attributes, and relationships that talk about how these attributes can do activities. Has is one, is a type, man is a type of a human being. All this becomes a relationship of building what is called a semantic network. One type of semantic network is called frames. What is special about frames? Rather than put in everything around, a frame was able to make it a much more smaller area. So it said, for example, you are having a workshop. In a workshop, you're going to have necessarily machinery, raw material, and finished products. What the machinery will be can change. What the raw material will be can change. What the finished product can be changed. What the operation that can be done can be changed. So all these are called slot. So a slot called machines is there and can be filled in with machine type 1 or machine type 2 or different machines. This is what we call a slot filler notation. So the commonly occurring values are there that's being filled up for the attributes in a relationship, the slot. This is the frame type. This is very useful in semantic network. That's why I've given this an example here. So there's an architecture, which means how do I join all these neural network nodes together? I can join them in different manners. There is something called a feed forward network. So these neurons that are there in a particular layer of nodes give an output to the next layer. So this neuron that are layer T will give an output to layer T plus 1 and nothing else. There's also something called a feedback. This is relevant today because our Nobel Prize winner was for a Hopfield network. So I'll tell you a little bit more as we go into this. So feedback system is where not only does the Tth layer give an output to the T plus 1th layer, the Tth layer can give output to the T minus 1 layer also. And sometimes the final layer, the output layer, can give an output that goes back to the first layer. It is something like a closed loop system for all you engineering people. You may be looking at it that way. So you have different architectures now. How many nodes are there? How many connections are there from neuron to another neuron? Now, along with all these connections, the most important thing for an artificial neural network is what is called a threshold. In a way, I spoke about it just now. Hopefully, I said what I'm talking about and the slides I'm showing you is interesting you people. The neurons in your brain and in the artificial neural network have a threshold level. If the input signal is below this threshold level, it remains quiet, asleep practically. But if the input level is going beyond this threshold level, it becomes excited, it becomes active, and it will itself produce an output that goes to the next layer of neuron. This is what is happening. So how do we learn? If we give an output and the output is wrong, then we are supposed to change our excitation points. By changing the excitation points, we're able to now give the correct output over there. Now, how do we change the excitation points? We don't actually change the threshold point. What we do is we try to give more weightage. So, for example, if your friend is calling you, you'll immediately respond to that. If somebody else is calling you, you might ignore. So the friend's voice or the particular signature tune that you give in the cell phone makes your brain become more active. So you're giving a weightage to that particular tone or that particular voice. Weightage is the main thing. So what do we learn here? We learn these weights. I hope I've been able to sum up the complete architecture good enough for you people to understand. So everything in this sub-symbolic computation is based on learning. In knowledge-based systems, you could put in some knowledge and then do learning on top of that. Here, everything is learned. It starts with random weights for every particular pair of inputs, but the correct weights are learned based on how it gives an output and gets a feedback saying this output is good or bad. Based on the feedback, it makes changes. So in sub-symbolic computation, all the knowledge is learned by the system. Neurocomputing attempts to mimic the structure of the human intelligence system. This neurons and synapses. So in our human system, we have something called a synapse. So from one neuron to another one, a neuron basically has got a dendrite that shows the output and axons that take an input. So once the input comes in, there's a neurocell. So the chemical systems inside the neurocell will decide whether to give an output or not. If the output is there, the output comes through this dendrite, and there is a gap between the dendrite and other neurons. So the output from this neuron is strong enough, it crosses this gap and goes to the next axons. That is how it works. So if it's trying to learn a required connection now between, listening to this and becoming interested in what is being said, then either this dendrite can release a chemical of a larger concentration, or it can actually move closer towards the axon. This is the learning that happens in the human body. And now to similarly do something like that in the artificial neural network, Every neuron is going to receive input from many other neurons. Each input is now multiplied by a multiplication factor, magnified by. This multiplication factor is representing the degree of interest or how much you're supposed to be. So this is what the effect that this particular input has on the neuron. So this degree of interest or the weightage is what we're talking of over there. The initial ones was a diagnosed disease. I gave you some examples. Mycin was getting the blood sample and was able to identify all the blood diseases. Induce was able to identify agricultural problems. Given example of what is happening in the farm, was able to work much using a learning mechanism, was able to work better than the agricultural experts itself. Design was doing designing new systems like computer network architecture and much more things were being done. Intelligent tutoring systems was being done to identify why the student was making a mistake. It learned something called a student model. This is actually my PhD work, was to learn student models. It can recognize handwriting. Today this is working pretty well now. Not still a student's handwriting, but most of the handwritings are actually possible. Another example of what we call Gen AI. A PhD work by Douglas B. Leonard was called AM. That software discovered Ramanujan's theories in number system. Ramanujan's theorems in number system. So different that even the mathematician had not heard of it. They had to go check in the library and say, oh, this is what Ramanujan had said. A lot of other systems today which can recognize the face, make recommendations to you, can do speech recognition, can do chatbots. So AI differs in conventional AIs, conventional systems by being non-algorithmic, and a big one that I try to highlight. The only system that actually discover the solution and then execute it up. All of the programming systems only execute the algorithm that has been given by the programmer. AI can discover the actual process methodology and be able to solve it itself. This is the advantage around here. So this is a cover up. I'll now add one more note there. Deep learning, that is what is being spoken of over here, and how Geoffrey Hinton is the other Nobel Prize winner in AI this year. He and his research student brought in a breakthrough in deep learning. So deep learning is a type of artificial neural networks where the number of nodes are much larger. And what it does is, see, in this artificial neural network, like I explained now, it has to find the correct samples to learn from, and it also has to identify what is the correct weight value to each of its nodes. Now there are two things like this. What was their breakthrough actually was to do this step by step. So that was able to solve the problem of deep learning. And today deep learning architectures are able to do a lot more than what the other architectures have been done. But I believe that there is a need for a synthesis between all the AI techniques. Sure, that was an introduction to what all has been done. If you permit me, I will then just show you what we have done in our company. Is that okay with everybody? If any questions are there, we can take it now.
You touched upon natural language processing, you touched upon, the previous self-supervised learning, etc. I was just figuring out, is there a connection between emotional AI, which is called affective computing, and neurological computing? You touched upon, for example, mutations, neurological computing, etc. So I was just curious, is there a connection between affective computing and neurological computing? The sense emotional AI.
I understand. Arunkumar sir, thank you for your questions. Very knowledgeable as well as very pertinent to what we're talking about today. I would like to differentiate it in two ways. Effective computing is a result of doing something. So applying AI towards understanding emotions is what effective computing is working on. How do we do it is multiple techniques. We can use genetic evolution techniques. We can use artificial neural networks. We can use knowledge-based systems. How do we do it is in multiple ways. So what we have spoken about more is about the technology rather than application. So how to achieve that? Today, of course, it is being done more using deep learning applications, but earlier on, they tried to do this effective computing by using knowledge-based systems also. Today, by looking at a person's face, they're able to recognize the emotion running in that particular person's face and able to respond accordingly. Sentiment analysis was being done without using neurocomputing by even a Python library quite a few years back. Based upon what passages you write, it's able to say whether you're happy, you're sad, you're angry, things like that. That has already been done some time back itself.
Is it possible directly apply this AI to the 3D printing or welding or composite manufacturing? where it is controlled by mostly process, how to interface this theory and to the practical. Because today we have a number of process-oriented components. So we reject our inspection and costly and other things. Can it help the AI in the initial phase itself to control?
Okay. Can I answer that with a demonstration of what we have done in my company? Can I answer the question? Sure. So I'll close this and see if I hope you're able to see this new set of slides.
Yeah.
Okay. So this is IKVAL Software's limited liability partnership around. So we have good capabilities in AI vision, natural language processing, predictive analysis, and conversational AI. So as I go through this, I will show you a particular application that we have developed, which is able to identify defects, including defects in welding, painting, manufacturing windshields. I will show you that. And maybe you can come back to me with more questions at that time. Will that be okay?
Yeah.
Sure. So we'll start with AI vision. And I'm starting off with exactly what your question is. So these are all products that we have developed in our company in 8 years. We started in 2016, around the same month. And this is what we have done in all these times. We started a little bit earlier, but the company got registered in November. So I'm saying it's November actually. So we can do things like identifying defects. We can also do things like counting the items. Some of the examples that we have done over here is to identify defects in the surface of products like fiberglass. One customer was manufacturing windshields for marine ships, because marine ships is superfluous. So this customer of theirs is in Amsterdam. So in spite of doing all their QA work over here and QC work over here, the Amsterdam customer will always come back saying, hey, there are some mistakes. So they gave me samples of these mistakes, simply taken through a cell phone. So I'm not asking for a high resolution camera. Taken through that cell phone itself, they gave me multiple samples. My application was able to learn and identify those defects exactly. So I've done this in painting also. I'll have some pictures at the end of the thing for welding too. So this was actually for somebody who's doing manufacturing vehicles. So like buses and lorries and such things they were manufacturing. So in their painting and welding activities, scratches used to come. The painting was done little less, or over painting was done. The welding was leaving welding marks over there. You'll be familiar with all these terms. So all this are application that is escaping their QC work. So we now built a solution where their supervisor will just walk through the complete surface of that particular body with a camera, give it to a laptop, and we give the answer back saying there is no defect at all, or these are the points where you have defects. So how is the input over here? Images of a surface taken very simply with either a digital camera or a cell phone camera. What can be identified? Scratches, dents, hits, overspray, spatters, dust rash, and we can also count. So there are cases where they wanted to count how many nuts are there on a particular surface. Sometimes while doing an automated process, they miss out putting in one particular nut. So we can identify how they missed out one particular nut, or things like that can be identified. I'm showing you some of the images in this. This was the windshield case. So this is the frame of the windshield, and you can see that there were defects being found here. You can see this defect over here, and in this particular one here, there were defects in this point too, in this particular point. We actually were identifying more than what the actual defects due to the background being something that is confusing the application in that respect. But what is required? Identify defects. So if there was a defect, all the defects are being found. You can see the defects are marked by these rectangles. These green boxes or blue boxes are here. Those identify the actual defects here. So you can see a defect at this location here. You can see another defect over here. Another one in this very, very minute defect, but that is also identified in all these cases. All this was being done for these marine windshields. This is for the painting and welding defects over here.
Maybe this is you are finding the defect after the product is made. Yes. I thought AI will tell the parameter what you selected is wrong. If you do this way, you will end up with defects. So don't do that. That sure. Type of instruction should come beginning based upon maybe many parameters and other thing. these defects can be found out by many ways. Why AI is required?
No, so this was missing the human eye, and that is why we had to find the AI. And I get your point. You want to be doing it before the defect happens. Yes, if a particular machining parameters and process parameters are given, and we are able, the application should definitely be able to identify when the parameters are not as expected. It should be done. I cannot answer directly because I don't have a realistic situation now. But if you can give me some situations that are there, I'm pretty sure my application can learn what is a correct set of parameters and what will not be an acceptable set of parameters. We can definitely learn that. One example that we have done is to predict. One example that we have done is to predict the EMI payments of customers. So this was a company that was giving loan to people to buy vehicles. So even after they've been onboarded, while they're making the payments, sometimes they falter. So based on the history of payments of a particular customer, you are able to predict exactly the next 3 months the person is going to make a payment or not make a payment. So they could do their fund flow analysis better, or what they call collection optimization. That is something that they could do. So given parameters, we can predict what is good, what is bad.